We ready to go? Okay. I'm going to make a link with Susanna because she finished by showing you that sparrow. And those sparrows are disappearing from your cities and my cities and from cities everywhere on planet Earth. And what I want to do over the next 45 minutes or so is to show you how you and I have fundamentally changed planet Earth and how cities are a major component of that change. So I want you to begin by thinking that you're an alien civilization and you're passing on the dark side of planet Earth. And over the past 2 centuries, you will have noticed something really fundamental happening to this planet, because now the night sky is ablaze with the lights of hundreds of cities with more than 1 million people living within them. It's a fundamental change. And I just want you to think about how you and I are changing the Earth around us. So let's think about a light bulb, an old-fashioned light bulb with 60 watts that burns a certain amount of energy every second. If you take one of those light bulbs in your house and think about how long that one light bulb must burn to burn through all of the energy that humans use in just 1 year, that light bulb will be burning until the end of the universe. For 450 billion years, that light bulb must burn. And then think about humans. I'm a geologist, so I'm thinking about how humans might preserve as fossils long into the future. What might be our record? The average human weight is 62 kilograms. So the average current weight of humanity is 450 million tons. It's a staggering figure. And if you just took the skeletons alone, because those are the bits that usually preserve in the fossil record, that's 72 million tons of you and I walking about on this planet at present. Let's just think about the numbers of humans. There are 7.4 billion human beings on planet Earth at present. It's a staggering figure for a single large species. Now let's put that 7.4 billion in context. Let's think about the populations of some major Polish cities, first of all. What about Warsaw? About 1.8 million people. It's a big city. Krakow, the city that we're in at present, it's about 750,000 people, about 0.75 million people. Katowice, about 300,000 people. So still quite a big city. Whoops. Stargard. Coming down the list now, we're down to about 70,000 people, so quite a small city now, large town. Why am I showing you the populations of some of your cities in Poland? Why is that relevant? It's relevant when you think about our numbers as a species relative to other species of primates, our closest relatives on planet Earth. Remember, there are 7.4 billion of us on this planet. How many do you think there are of the next most populous primate species on planet Earth? The next species after us, the next of our relatives. Let's have a look. The next one is the Bornean gibbon, with about 300,000 people. That's one human city. That's Katowice. That's the next most populous primate on planet Earth. Let's come down a bit. Chimpanzee, the iconic relative of humans. That's Sosnowiec. One human city. One city in Poland. Let's go down the list a bit more. The Bornean orangutan. Well, that's a fantastic species. That's Stargard. That's one small Polish city. We can go down and down and down. The Sumatran orangutan is one town. And that beautiful primate looking at you out from the picture is the golden lion tamarin. It's one human village. So you can see that you and I are actually 99.9% of all of the primates on planet Earth. It's definitely the planet of the apes, but we're the dominant ape. Okay, if we think from our numbers, the 7.4 billion of us, then in fact we are a global force, and I'm going to demonstrate to you that we really are a global force, how might you and I be preserved in the fossil record going way into the future? So we have to travel forward 100 million years in time. And how might your and my impact on the planet be quantified? Is our impact so great that we fundamentally changed the Earth system? Now, to do this, we have to think about time. The birth of Earth, 4.5 billion years ago. The formation of the crust. The formation of the oceans, 4 billion years ago. And almost as soon as we have evidence on planet Earth for oceans, we have evidence for life. So Susanna talked about human timeframes of 100 years. But you're part of an unfolding story that's 4,000 million years old. There's been a biosphere on planet Earth for 4 billion years, and we're part of that. So when we're trying to measure our impact, we have to think about that impact relative to the whole of history on planet Earth. Now, this is a horrible slide. I don't want you to assimilate the information on it. And it's taken geologists about 200 years to actually make this. But when we're dealing with these enormous packets of time, 4 billion years, it's difficult for us as humans to comprehend them. So what we try to do as geologists is to break it down into smaller packages of time. And each one of these packages that you can see here represents a major change in the state of planet Earth. Something really fundamental happened to define those boundaries. You can see it's going back from the present here on the left-hand side, way, way back to 4 billion years ago. Now, you and I would know the Mesozoic era, this period from about 65 million years ago to 250 million years ago, as the time when dinosaurs walked on planet Earth. And of course, that interval of time ended catastrophically about 65 million years ago with a large meteorite strike in the Gulf of Mexico. So that stopped that period of history. And then evolution continued, and we have all of the life that we have in this time interval. Well, what I and Jan Zalazevich and Colin Waters and others at Leicester University would now suggest to you is that you and I have so much changed the Earth that we should add a new time interval to this geological timescale. And at the top here, where we have the Holocene that we're supposedly living in at present, we now live in the Anthropocene, a new time characterized by our actions. And I hope I can prove that to you in the rest of this talk. Now, the idea of a changed system is not new. It's been around for a long time, certainly since the 19th century. The Milanese geologist Antonio Stepani in the 1870s was already suggesting that humans had fundamentally changed the Earth. Well, the idea didn't really take on in science. It lay moribund for over a century until Dutch scientist Paul Crutzen resurrected the term in the year 2000. And since then, it started to take on a lot of different meanings. The source of the term comes from Paul Crutzen. Now, if we're going to ask, how have we impacted on planet Earth, we have to think about what it is to be human and what it is that characterizes us and enables us to be so impactful on the planet on which we live. And that's a difficult question because we've left a fossil record, both in our skeletons, but also in the materials we use, stone tools, that goes back over 3 million years. So is this the beginning of our impact on planet Earth? Is this where the Anthropocene begins? Or is it the time in our history when we start to leave our African homeland and start to colonize the rest of the world? This human species started to do that about 2 million years ago. It left Africa and colonized most of the old world. Is that when we should draw a boundary for the Anthropocene? Or should we draw the boundary where we become behaviorally modern, where you and I, 70,000 years ago, are thinking in exactly the same way that we're thinking at present? We have evidence of that from cave sites in southern Africa. Is that the time when we have become the dominant entity on planet Earth? Or we can see how our impact starts to unfold over the planet. in a much greater, much more dynamic way, from around about 15,000 years ago, when humans, for example, arrive in North America. Very soon, all of these wonderful large animals disappear from the landscape in a matter of a couple of thousand years, probably because you and I hunted them to extinction. Gone forever. Or might we define our impact at the time we invented agriculture in many different places on planet Earth, from the Americas to the Fertile Crescent to China? This is happening about 10,000 years ago. Or is it the time when we invented industry? We built the first iron bridge. This iron bridge is from about 200 years ago. It's got a span of 60 meters. And now we build bridges with a span of 4 kilometers. In 200 years, that's an incredible change. Or we might think about the way in which we are impacting on the rest of the biosphere, the way we impact on other animals and plants. So all of these species that you can see here, they've all gone extinct because you and I have made them go extinct. So this one is the classic, of course. It's the dodo. It's a species we all think of as being exterminated by humans. Then we have the Caribbean monk seal, a wonderful animal that we lost half a century ago. The beautiful Yangtze dolphin that we lost only a decade ago. They're all evocative of our impact on the planet. And does anybody in the audience know what this one is? This is one that we've exterminated in the wild too. This is the smallpox virus, also exterminated by humans. So we might use one of these to define where our impact is. Maybe the Yangtze dolphin disappearing. Yeah, that's evidence of human impact on planet Earth. But actually, although these are significant individually, they're not significant in the global context. So given this really long record that we've been on planet Earth as a group of species for about 3 million years, where are we going to identify our maximum impact? I nearly fell off the stage. We can't use any of these earlier signals, and we can't use them because they are localized. And for me as a geologist, I have to look for a signal which I can find everywhere and which I can identify as indicating a very, very quick interval of time. So a massive asteroid striking planet Earth is a disaster for planet Earth, but it's brilliant for me because then I can define my boundary very, very quickly. And that's the kind of thing I'm looking for. So it's this I'm after. I want something that is so important, so huge, so gigantic, that I can recognize it everywhere on planet Earth, and I'll be able to recognize it long, long into the future also. So I want us to consider the Anthropocene from the perspective of cities, because that sits very well in the nature of the talks that we're going to see today. And I want you to think about the impact of cities on planet Earth and the way in which they may leave a very distinctive geological signal of you and I long into the future, hundreds of millions of years into the future. Now you might say to me, well, cities have only been around for about 7,000 or 8,000 years. They're a relative recent innovation in terms of the human impact on planet Earth. Well, they may only be 7,000 or 8,000 years in their duration, but they signify something really dramatic happening to the whole Earth system. They are the engines now of change on planet Earth. I'm not going to show you many graphs, but I am going to show you this one because it's really telling. What I'm showing you here is the way that humans are consuming energy on planet Earth. And these are vast amounts of energy. These are exajoules. And that's an accelerating change. And you can see that much of the energy, most of it, in fact, is being expended in cities. Now, if you add up all the energy that humans use, from nuclear sources, from hydrocarbons, from coal, and you add that amount of energy to the amount of energy that we extract from the biosphere, so from plants and from animals, when you put it all together, it's nearly as much as all of the energy available to all plants on planet Earth. So one species uses nearly as much energy as all of the plants above ground are using in a year, generating. That is staggering for one species. and completely unprecedented in 4 billion years of Earth evolution. Okay, so if we take cities as being something really dramatic and dynamic, how might they preserve? What would I look for as a geologist? What I need to find is what structures in a city, like Krakow, would preserve. What would leave a geological record? So as a geologist, what I try to do is define different kinds of fossils. So some fossils are body fossils. They're the skeletons of animals or plants that lived long ago. This is a trilobite from the Cambrian period, from 500 million years ago. And what's preserved there is its skeleton. So that's a body fossil. Sometimes we don't have the animal or plant itself, but we have a trace of what that animal or plant left. So here you're looking at river sediments from 400 million years ago. And into those river sediments is this 1 meter long burrow. It's an animal burrowing down into this ancient river. And that animal was a millipede, but it was a 2 meter long millipede, not the kind of millipede that we might meet on the way home today. So this is this giant millipede. Probably wasn't having a battle with this animal, but it left this trace. That's a trace fossil. And then there's another group of fossils that we defined just a few years ago, which we called techno fossils. These are the artifacts that you and I generate that might fossilize. So let's think about this Japanese lunch in Kyoto. Think about what might be a techno fossil here that would preserve. So the porcelain bowls, that's got good preservation potential. There is the material of the basket, the wooden material, that might preserve. The tray, the lacquer tray, but also the food. The food is something that you and I have made too. And it is a potential technofossil, but it's not going to have a very long life, I'm afraid, because I ate it in about 1 hour after this. So the food didn't survive. But the other components are potential technofossils. What might preserve then? What might we find in the fossil record of us over long time frames? What will be permanent and what will be ephemeral? So to do this, we have to look at what's preserved in the past. So first of all, I'm going to take you to a lost village in the English Midlands, to an Iron Age hill fort. You can see the boundaries of the fort, and inside there was a village, people living there 2,000 years ago, and they were living in houses like this, round houses. Those round houses are made of locally sourced materials. Most of those materials are not long-lived. You wouldn't expect to find them fossilized in the geological record because they will rot and decay. But something has survived. So 2,000 years later, the archaeologists can still find the furrow that was dug out around those round houses. And in that furrow, in that excavation, you can find bones and pottery and sometimes other artifacts that were cast away by the people living in this village. All of those are technofossils, and all of them are preserving over a long time frame. Let's come forward in time to a classical city. What might preserve from a grand structure like Ostia in Italy, and again that we could find as a distinctive signal of humans long into the future? Well, we could look at the modification of the harbour of this city around about 2,000 years ago, with the construction of the Trajan harbour and how it modified the river Tiber as it flowed into the Tyrrhenian Sea. And you can see a distinctive geological signal of these changes. So don't worry too much about this figure here, but do have a look at this one, because this one is showing you the sedimentary record as it's been cored in that river, going back in time from the top to the bottom. And at the bottom, you find the natural signal before humans have impinged on these natural processes. And above that, when the harbour is built, the sedimentary style, the way the sediments are forming, changes completely. And it's not just that the sediments change completely, the things in the sediments change. So now we find pottery and bone and other artifacts, again, as a direct signature of human influence. Let's come forward again to a modern city. This time we're in Hong Kong. And now we're going to flatten Hong Kong Actually, I really love Hong Kong, so I don't want to do that. But we're going to flatten it and see what happens. Crunch. So now we're making stratigraphy, which are the layers of sediment and rock that accumulate on Earth over time and give us that geological record. What's going to happen? At the bottom, we're going to find our stone implements from long ago. And then above them, metals, and right at the very top, plastics. And when we get to the top, when we start to find plastics, then we start to find a global signal. Because those plastics, we can find them in Krakow, in London, in New York, in Shanghai, in Hong Kong, everywhere. And very suddenly they appear really from the middle of the 20th century, everywhere. Now, we don't have to think about what is being buried and deposited. We have to think about whether, when it gets buried and deposited, it will stay there too, or whether it will be eroded away. If it's eroded away, it leaves no record of us whatsoever. So we might think of this wonderful building in Athens as being a symbol of the birth of Western civilization that we can all relate to. But I can tell you as a geologist, it will not preserve. It sits on the top of a hill. It will be gone. It will erode back into the rock succession. No matter what you or I do, it will be gone in the future. We need to look for areas that are subsiding that will actually preserve the record of you and I in the 20th and 21st century. So a place like Shanghai in China might be a good place to look because it's sinking. It's a huge city of over 20 million people, but it's built on coastal sediments. And because water has been extracted from those sediments, the city is sinking down. And because so many buildings have been built on the city, it's sinking down. It's sunk about 3 meters, actually, in the last century. That's great for me. It's really good because it means this city will sink and it will be preserved. It will be inundated with sediment. It's not so good for the people who live in Shanghai, though. So, and other coastal cities, of course, have this problem too. And of course, it's not just that Shanghai is sinking, but because you and I have been using fuels that generate carbon dioxide, and we've been changing the atmosphere and the oceans, then sea level will rise too. And this is inevitable. This will happen in the next 100 years. Sea level will rise by perhaps a meter. So Shanghai has real problems. Not just Shanghai, but many cities around the world. All of these cities potentially will be inundated by the sea. That's really good for me because it might give me a global signal of cities that preserves long into the future. It's really bad from a human perspective. And just think of one country, Bangladesh. If you raise sea levels by 1.5 meters, quite possible in the next 200 years, Bangladesh loses 25% of its area and displaces about 20 million people. Where do those people go? And where do the other billions of people go who also live in the coastal zone on planet Earth? Or I might think of zones of unusual accumulation to define where I put my Anthropocene boundary. I could take the rubble that accumulated in Berlin after the city was decimated at the end of the Second World War. Of course, all that material was gathered up to make the Teufelsberg. This is the Teufelsberg in the background here. It's a huge structure. It's a very clear indication of human destructive power, and it will preserve long into the future. For architects, I want you to think about the way that you are redesigning planet Earth and the way in which you too have had a massive impact on the potential stratigraphical signal of the Anthropocene. So now we need to look at the evolution of architectural patterns in cities over human timeframes, historical timeframes. If we went back just 100 years, you would see very distinctive architectural styles in different cities. Krakow is clearly very distinctly different from London in its old medieval core. It's very distinctive. Now, as a geologist, I could recognize those patterns. If I came back in 100 million years, I'd be able to recognize a clearly Polish culture and a clearly British culture And then what happens? In the middle part of the 20th century, the international style takes hold. And now if you look at the buildings being erected in your beautiful city, in Krakow, or anywhere in the world, they're rather similar to the buildings that are going up in Jakarta, or in London, or Shanghai, or New York. And they're made from the same materials, from concrete, from glass, from steel, that's traded across the world. That will leave a huge and very distinctive signature of you and I, and it's almost instantaneous from a geological perspective in a few decades. So the top is London, the bottom is Jakarta in the 21st century, and this is England and Central Java in the 9th century. They're quite different. The growth of cities in the 20th century especially is associated with this huge massing of people. That massing of people had profound other impacts on cities and the artifacts that those cities will leave behind long into the future. So I showed you a burrow from 400 million years ago made by that giant millipede burrowing into sediments. And then from the 1860s, a new form of burrow system starts to emerge on planet Earth associated with rivers. This is the burrow system of the London Metro. It begins in 1861. Of course, it's a riverside succession of boroughs. It's built around the River Thames. But it's an order of magnitude greater and an order of magnitude more complex than any trace fossil left by any animal on planet Earth in the deep past. Another preservable signal, not least because this metro system actually digs down into the bedrock, the solid geology below, which means it's permanent. It's there for tens of millions of years. And it spreads across the world. It starts in London in the 1860s, but look now, it's everywhere. There are metro systems on all continents apart from the Antarctic. Urban metro growth is particularly strident in the later part of the 20th century, and it tracks things like human energy use in those urban areas. So these metro trace fossils that will persist long into the future are a really good marker of your and my impact in the 20th and 21st centuries. And that dovetails with one other parameter, something which is uniquely human, the way in which we use the force of splitting the atom to generate energy, sometimes in constructive ways and sometimes in very destructive ways. Again, the detonation of the world's first atomic bomb in the New Mexico desert in 1945, the middle of the 20th century, when we see all those other big changes like the spread of metros, change in architecture. So we can start to track these events and link them across the whole of planet Earth. So I hope that I've convinced you, first of all, that your impact is immense and traceable everywhere, and certainly from the middle of the 20th century is so profound that it's altering the Earth system. In the last part of this talk, I want to show you how you've modified every component of the Earth, the hydrosphere, the atmosphere, the landscape, but most importantly, the biosphere. And I'm going to focus on the biosphere because I'm a paleontologist. So I study the evolution of the biosphere, of all life on planet Earth, over the last 4 billion years. I want to show you that what you and I have done is profound. It's profound by any change in geological time. It's not profound in this way. So in the 1950s, there were a whole series of Hollywood movies with giant tarantulas and giant ants attacking Los Angeles as a result of those atomic bomb tests in the New Mexico desert. That's a kind of facile way about thinking of our human impact. It's actually much, much greater than this, much greater than gigantic ants. So one thing you might think about straight away is that you and I cause extinction. Sparrows leaving cities, for example. It's a local extinction, a local extirpation. And extinction rates are certainly above background levels, but they're not yet at levels that will cause a mass extinction. And this is also not unique. We've had mass extinctions in the past. We had a big one at the Cretaceous Tertiary boundary when the dinosaurs went extinct. So although extinction's a big component of what you and I are doing, it's not the unique component. So what might be entirely unique about what you and I have done on planet Earth? I'm going to give you 4 things. You can, I hope you'll argue back with me and tell me whether you believe them or not. The first thing, and this is really incredible, and it's part of the way that we have to feed our growing human population, is that we take about 25% to 40% of all of the energy of plants. And we use a lot of that energy to feed our domesticated animals. I just want you to look at the figures here. 175 million tons of carbon by dry mass is you and the animals that you eat. And all of the wild animals are 5 million tons, less than 5%. So everything else is squeezed to a tiny percentage. That's the first way that we've changed everything. And we don't just use the energy from the primary part of the biosphere, we use the energy from the fossil part of the biosphere too. So these are the bodies of animals and plants that died and rotted away millions and millions of years ago. We take that energy too, and that's an incredibly accelerating use of energy, well over 500 exajoules at present. So there's all the energy we take from the biosphere and all the energy we take from the fossil biosphere to power our civilization. Not just the land. We are unique in history on planet Earth as one species that dominates not just the land, we also dominate the oceans. We dominate the entire biosphere, the land and the oceans. The figures are staggering. 160 million tons of fish products consumed by you and I, well, not individually by me, but by you and I as a species on planet Earth each year. Staggering figures. My second parameter, the first parameter is the kind of way that we take energy. My second parameter is the way that you and I have moved animals and plants across planet Earth. So it's not really the invasion of the body snatchers, it's the invasion of the ecosystem snatchers. This is a classic example, the rabbit. It's an animal that we've translocated everywhere on planet Earth, sometimes causing huge damage to local ecosystems. Now, these processes have also acted in the past in geological timescales. So about 3 million years ago, South America bumped into North America, formed the Isthmus of Panama. South American animals went north, North American animals went south. So we know these processes exist in the past, but the difference at present is that you and I have done this on a global scale. We've moved animals and plants everywhere on planet Earth. I think this is from a fairly old scientific paper, nearly 20 years old now, but it's still really dramatic. Just look at the number of introduced species, of plant species to New Zealand. There are nearly as many introduced species as there are native species. Now, New Zealand is an isolated landmass. This cannot happen unless you and I do it. And this is a global signal. So this is the second global signal. The first is energy. The second is the way in which we completely moved everything around the planet. And you can see that in the most remote places. So this is a sinkhole, a cave system on one of the Hawaiian islands. And around about 1200, we start to find Pacific rats appearing as fossils in the sediments that accumulated in that sinkhole. Those rats got there because humans brought them there. And that process can be tracked in that sinkhole right through to the 20th century. You can see the way that the local fauna and flora gradually was completely changed by humans. So that in the 20th century, we brought in the giant African snail. The giant African snail in Hawaii? How did the giant African snail get to Hawaii? And the South American cannibal snail, which does exactly what it says. And of course, these organisms have radically changed the snail population on these islands. In fact, they've decimated the local snail populations. The third parameter is the way that you and I have modified the landscape around us. So the city is a classic example of this. It's an example that excludes the biosphere. It's the anthropocization of the landscape. So I want to show you the work of Earl Ellis at the University of Maryland in tracking the way that humans have changed the landscape. So this is back in 1700, and the definitions at the bottom are the definitions of the ways, different ways in which humans have modified the landscape. And you can see that about 5% of landscapes are used, they're urbanized in the early part of the 18th century. Come through to the 21st century, you and I have impacted on 75% of the ice-free landmass of planet Earth. 75% is human-modified. I have to give you this quote. This is from Earl Ellis. The world is no longer dominated by natural ecosystems with humans disturbing them, but is dominated by human systems with natural systems more or less embedded within them. So you cannot show me a natural landscape. Find me a natural landscape in Poland that has not been impacted on by humans. I challenge you. If you can, I'd be really happy. I don't think you can find one. And in those ecosystems, we modify those organisms. So we can take plants and we can completely change their genetics so that they increase their production. Super plants to not so super chickens. This is what you and I did to chickens in 4 decades. And this too has left a geological signal, because I could find these anatomical changes in landfill sites, for example. And the last parameter of the 4 parameters that I'm going to give you is the technosphere. This is an emergent system. It's the idea of Peter Haff at Duke University. It's you and I, all of our cultural connections, all of our technological connections, all of the technology that sustains us. It's growing out of the biosphere. It's a new component of the Earth system that we never saw before. And it's parasitic on the rest of the Earth system. At the moment, it uses materials without recycling them back. And that's the real danger that we face as a species and as a biosphere. So these are the arterial systems of the technosphere, of coal and oil and other materials being moved around the planet like a massive engine consuming energy. I just want to give you one figure, which is really amazing. The country that we associate with the skyscraper, the USA, used 4.4 gigatons of concrete to make its skyscrapers in the 20th century. Well, China beat that in 3 years in the 21st century. It beat it dramatically. This is an accelerating process. And linked to that is the explosive diversity of our technology. Look around this room and tell me where you see the biosphere. Susanna showed some wonderful pictures of architects bringing the biosphere back into the buildings. Apart from you and the billions of bacteria that are living on you and in you, I don't see the biosphere in this room. But if you look around you, look at all the technological species, the computers, the audiovisual equipment, the televisions, the chairs, the carpets, the buildings. You have made space here for technology to expand into. No space whatsoever for the biosphere. We're excluding it from our ecologies. Of course, all of these changes dovetail again with this dramatic change in the way that we use energy in the 20th century. I'm nearly finished, but I want to do one thing that a scientist should never do. Because a scientist should never try to predict the future. It's really the way to set yourself up for a fall. But I'm going to try and do it anyway. Because as a geologist, I'm really lucky. I can look back at 4 billion years of Earth history, and I can look at the fossil record. I can see an extinction event there. I can see what happened next. I can see the biosphere recover. So I'm going to try and use that knowledge to tell you where I think planet Earth is going to go in the very, very near future. There's a wonderful book by Dougal Dixon. It's called After Man. It should be called After Humans, of course. But in this, he imagined a mass extinction. And from the animals that were left, he imagined what might evolve into the future. So you and I have caused a mass extinction. We disappear from planet Earth. Organisms, penguins evolve to become whale-like animals. Rats evolve to become walrus-like animals. This would happen. And the species which is most widely distributed, or the species group, is a group of animals called the rabbits. Rabbits. There are big rabbits, little rabbits, rabbits that live on mountains, rabbits that live by rivers. They're really distinctive. There are a whole range of different types of morphology, but they all have really big, long ears. What do you think the rabbits evolved from? Somebody tell me. Rabbits. And this would happen, almost certainly. I'm going to leave you with 3 scenarios for where we might be going in the not-too-distant future. The Anthropocene, this big experiment that you and I have engaged in, becomes a short-lived experiment with planet Earth. Becomes unsustainable. It precipitates a mass extinction, quite likely in the next 100 years or so. And of course, we suffer as a species as part of that. Human numbers would be dramatically reduced. The biosphere would be devastated. And as a species, we would never see a diverse biosphere again, because it takes about 10 million years to repair the biosphere when these mass extinctions happen. The second one, and this is seriously possible too, is that in fact the technosphere is the next stage of evolution. That biological evolution is now being overtaken by technological evolution. Hopefully that technological evolution will be benevolent to you and I. It's one possibility. I don't really like that one. I don't like the first one, and I don't like the second one. I like this one, which is why the people assembled in the room to speak to you today are the people who can drive these major changes. Because the third state, and the one that we have to evolve to, is one where the technosphere and the biosphere have a mutualistic relationship that is beneficial to both. And if we don't do that, we end up with the other 2 scenarios. So this is the one that we want to develop. But even then, this is my closing thought to you, if this happens, if we evolve a system where the technosphere and the biosphere behave together mutually, you and I have fundamentally changed planet Earth forever. And this change is as great and as fundamental as any change in 4 billion years of evolution on planet Earth. You truly are an agent of global change. Thank you.